All right, so this is the heats of formation, and this is the longer way of doing it, sometimes known as the indirect way. And this is where we use tables from a textbook. We will get it from the index in the back of a book, or sometimes it's like I have, it's in a textbook right here of table 6.3. You can see right up here that it gives us some information about all the standard heats of formation. And if you notice, a lot of the elemental forms that are at 1 atmosphere, approximately 25 degrees Celsius, in their most stable state. So calcium at 1 atmosphere of pressure and 25 degrees Celsius will be a solid, and we say it's the most stable state, so therefore we give it a number of 0. Where the next one, calcium oxide right there, is not stable, and therefore in order to create that, you would need to combine a few things, oxygen and calcium, and in the creation of that, it would give off negative 635.1 kilojoules per mole of energy. And we're going to see how that works right here with a pretty simple reaction. And the reaction is taking a look at a carbon in its standard solid state at 1 atmosphere, 25 degrees Celsius. It's also known as graphite. Hydrogen, on the other hand, is a gas. And because both of these are in their most stable states, they have numbers of heats of formation of 0 for each of those. So what we can do in trying to calculate how much energy is either gained or lost in the creation of the last thing, which is our product, CH4, we have to use all 3 numbers. And this is a fairly simple one to do because there's a bunch of zeros and then finally that one negative number. So we say this number is 0 in kilojoules per mole. And the same thing goes for this one here. So they're both 0. But this one right here is negative 74.9 kilojoules for every mole. And the nice thing about this here is we're going to have to balance it first. So it's a 1-to-2 relationship. The important thing here, though, is this right there. Because if we're saying that we needed 2 moles of hydrogen, it doesn't impact our final product, and our final product is really what we're looking for. And therefore, it's in a per mole basis. So therefore, in order to create a methane, 1 mole of methane from carbon in its form solid graphite and hydrogen, but we need 2 moles of that, we would be able to give off, or this would be an exothermic reaction, by negative 74.9 kilojoules per mole of that methane being produced. So that's a fairly straightforward one. If we take a look at this next one, we find we're creating 2 fairly simple products. One is 1 mole of carbon dioxide. The other one is 1 mole of nitrogen oxide. And I have some heats of formation at the top here. So for the first one, so I pull these heats of formation out of our textbook. And for the first one I'm looking at right now, I see negative 110.5. And these are in kilojoules per mole. But I'm not forming carbon monoxide. It's going to be one of my reactants. So this number is actually going to be positive 110.5. Again, from the textbook, I always see that my elemental form of oxygen here, which I only need a half of because I only need 1 more oxygen to make carbon monoxide into carbon dioxide, I have a 0. So I don't care about the negative or positive side if it's on the reactants or product side. And then finally, carbon dioxide. I see in the textbook that it is a fairly large number of negative 393.5. So that's the only thing we know from the textbook. So therefore, we have to say, well, if we're making carbon dioxide, that's how much energy would be given off when it's formed. But if we're making it with oxygen and carbon monoxide in this situation, what is the total energy? So I now combine these, and I always like to say combine them because I have to think of my positives and my negatives. And therefore, when I combine these, I get a fairly simple number of 200, negative 283 kilojoules per mole. And how many moles do I have? I only am making 1 mole here, so therefore that is my final number from making carbon dioxide from carbon monoxide and an oxygen using my heats of formation. The one right below it is a very similar one. I see N2 is 0, so I can throw that in there fairly quickly. I know oxygen from the previous one is 0, and nitrogen monoxide here is positive 90.3. It is on the product side, so therefore it is going to stay at a positive 90.3. So therefore, I'm just combining these, and it's fairly easy to say. I only need, again, 1 nitrogen, 1 oxygen, so therefore that's why I took halves of those, of the N2 and the O2, and therefore in order to make my 1 nitrogen monoxide, it would be a positive 90.3 kilojoules per mole, and again, I only have 1 mole, so that makes it fairly simple. So there you go. And I'm going to use these two for the next problem. So in the previous problem, we found that in making carbon dioxide, it would be negative 283 kilojoules per mole. In making nitrogen monoxide, it is a smaller number of 90, I think it was 90.3, positive 90.3. So therefore, I'm going to use these numbers now, and there's no way I could take a look at my much larger reaction here and figure out, well, how much energy is it going to take, or is it going to give off, or is it going to consume in order to make a carbon dioxide and a nitrogen gas from a carbon monoxide and a nitrogen monoxide. So I'm going to use a combination of things. I'm going to use the two reactions here, and I'm going to switch them around a little bit too in order to make them work. So what do I need to do? I need to take a look at my products and my reactants, and I see that in the previous problem that I did, I have nitrogen monoxide, but it's a product. Over here in the much longer reaction, I see it's on the reactant side. So in essence, I need to get that onto the reactant side. And what we talk about in class is we talk about, well, we can flip this around. And if we flip this around, instead of making nitrogen monoxide here, we're going to be using nitrogen monoxide, and we're going to change that sign as well from positive to negative. And what that hopefully is going to do is going to leave us, when we use the reaction above it, the carbon monoxide and the oxygen making carbon dioxide, and hopefully we can get rid of some of the things that we don't want, which is we don't want oxygen on the left-hand side or the reactant side. We don't want nitrogen on that side either. We see that we want nitrogen all the way over there. And like I said, we want to try to get rid of that oxygen. We also see we have carbon dioxide there, and that's on the exact side that we want it. We also see we have carbon monoxide on the exact side that we want it. And again, I did not want this oxygen either. So we have to try to figure out how we're going to get rid of a few things, and that's where it becomes kind of interesting to see how we can flip equations around. So I'm going to get rid of some of this so it doesn't confuse us. And remember, I can flip positives and negatives around depending on how I use it. So first thing I want to do is I want to rewrite this bottom one right here. So this one right here. And I want to flip it around. So I want to say, okay, well, my NO as a gas can be broken down into 1/2 of my N2 as a gas, and I can make also half of a elemental oxygen if I reverse that sign there for, and if I do that, I can get 90.3 kilojoules per mole of energy out when I break that down. And the one right above it, I'm going to rewrite it, but this time I'm going to keep it the way it is. So I'm going to say, well, carbon monoxide right here as a gas, and 1/2 my oxygen as a gas will create carbon dioxide as a gas, and I will be able to get out of that reaction 283 kilojoules for every mole I have. And what I remember my math teacher telling me, if I want to get rid of things, I have to subtract them. So let's think about, I'll use a green here. If I want to get rid of this, I will subtract it from that right side. So if I subtract whatever I do to one side, I do to the other. So if I subtract, well, half an oxygen gas from the right-hand side, I do it to the left as well. So in essence, I'm getting rid of these, which is nice, because I do not want that in my reaction. And then what I see I have left, I see I have my NO as a gas, I have my N2 as a gas, I got my carbon monoxide as a gas, and my carbon dioxide as a gas. So it looks exactly like what I'm looking for as my final product, which is right here. And it even has the 1/2s in the exact place which I need, which is right here, that 1/2 N2. So if I were to just rewrite everything now, and I'll do it in black, I have my CO as a gas, my circled, I'll circle it again, my circled nitrogen monoxide as a gas, and that makes my carbon dioxide as a gas, and I'm left with this right here, that 1/2 plus 1/2 N2 as a gas. And I got exactly what I want there. So how am I going to use these? Remember what I said, I just like to say I combine them, and since they're both negative numbers, they're going to combine out to, when I add these up, 283, a negative, and a negative 90.3, that should give me negative, what, 373.3 kilojoules per mole, and the number of moles work out as well. So that's the amount of energy that I'm going to give off when I create carbon dioxide and 1/2 of a molecule of N2 from reacting a nitrogen monoxide and a carbon monoxide. So that's how you use heats of formation, and you combine the energies, but you can flip reactions around if you need to, but when you do that, you have to change signs. Hopefully this helps. Good luck.